All right, everyone, welcome back to Mastering GLSL in TouchDesigner. So today we're going to be taking a look at fractals. Um, Fractals are really cool, and here's an example of some of the stuff we're going to be looking at and building later on in today's lesson. Obviously, before we do that, we're going to take a look at some slides and go over some of the conceptual stuff that's required for us to really be able to understand and capitalize on all of the uh, good information about fractals. So, with that said, let us jump into the slides and we can get things going. So again, Mastering GLSL in TouchDesigner. My name is Blake Heckerman. I'm a new media artist exploring how technology alters human perception and how we connect with each other. And I'm really inspired by the natural world, all of the kind of deep organic patterns, lots of complexity, some really cool stuff. So I love to kind of evoke that through cutting edge computer graphics and machine learning, which I use to build interactive installations. A couple examples of those interactive installations and large scale facades are here. Again, all of these are built using a lot of the concepts that I've talked about in this course so far, and we'll talk about later. So, yeah, just wanted to kind of give some context there, and now we can get into the meat of this lesson, which is going to be fractals. So, what's a fractal? Well, fractal is many things, but the best definition is a geometric shape or a mathematical set that exhibits self-similarity at various scales. What that means is that as we zoom in or out of a fractal, its structure is going to repeat itself. Now, I think everybody's probably pretty familiar with fractals, so I imagine this is probably not the first time you're hearing about this, but good to have a common vocabulary anyway. And so then, what properties do fractals have? Well, there's infinite complexity, agnostic to scale. What that really means is that you can have an infinite zoom on your fractals. There's a fractal dimension, which is known as the Hurst exponent, which is normally denoted with a capital H. And that is basically a measure that determines how much recursive self-similarity there's going to be. And then finally, the actual definition of the fractal itself is almost always done via a recursive or an iterative definition, which will make a little bit more sense as we go through them in some examples later. So here's just a picture of a Julia fractal, one type of Julia fractal. And yeah, I guess before we get into it, because I'm so inspired by nature, I wanted to have some examples of fractals in nature. So here we have some of those. You can see the phyllotaxis in the way that plants grow. Snowflakes are a classic example of a fractal. This conch shell. And then the ones that I like the most are these kind of river system fractals and also coastline fractals. And then this one in the center here is actually a macro view of bubbles. And so all of these exhibit that same type of fractal behavior, and I think it's just super fascinating. So now, fractal math. And I will say, this is going to get a little bit more intense than all of our lessons so far have, at least as far as the math goes. And the reason for that is that many fractals use complex numbers in their definition. And complex numbers are a whole thing that we will talk about. And it's not actually too scary, so don't get too stressed out. But it is going to require a little bit more math than we've really had to do so far in this course, which I'm personally very excited about, but I understand that it can be uncomfortable. So bear with me, and I think we will be able to learn a lot of this stuff without it getting too painful. So with that said, our complex functions our fractals use complex numbers, which really means complex functions, and the convergence or divergence of a recursive or iterative set of calculations, which is generally called a series in math, is going to determine whether or not a point belongs to a fractal set. And so that probably doesn't make a ton of sense right now, but it will make a lot more sense in just a few minutes. So bear with me. And then the convergence and divergence, or divergence, is normally visualized by using some distance metric, but can also be directly visualized. And we'll talk about all of that in a second as well. So, complex numbers crash course. I told you it was going to be a little bit more math, huh? So, let's just demystify a few things forthright. Complex numbers are called complex because they have a imaginary part. And imaginary numbers are basically numbers that have a component that is the same as the square root of -1, which is called I in the math world, or the imaginary number. This is an entire kind of discipline in number theory, and it really is not something that I think you need to worry too much about. It's more that the term is one that you need to be familiar with and not get too freaked out about when you see it. So complex numbers and imaginary numbers are things that we're going to use in this lesson, but try not to get too bogged down in the terminology and think more about the application, which will be much more straightforward. So complex numbers are expressed with this form: z equals a plus bi. And so there, z is a complex number, and a plus bi is the real component in a, and the b times I, which is known as the imaginary component. And what that means is that we can actually represent complex numbers on a plane, 2D plane, with the real component visualized here on the x-axis, and the imaginary component, really the coefficient, visualized on the y-axis. And so right here, 3 plus 2i, that's kind of where this complex number would fall on this plane. So that is basically the foundation that we're going to be using. So everything from here on, we're going to be thinking about numbers in a complex plane, and our kind of xy coordinates in our UV space, or like our pixel shader, are going to be representing a complex plane for the duration of this course. Now, the other thing that I need to mention, and I hesitate to do this, but it is necessary to fully comprehend all of the logic that we'll be implementing. Arithmetic with complex numbers has special rules. And the reason for that is because these numbers have imaginary components and real components, and we need to treat those components separately. So I have pasted some formulas here that may look a little bit intense, but really are not that bad. For those of you that are familiar with algebra or calculus, we're really just looking at kind of distributing the polynomials, basically. And so you can see that we're describing each of those polynomials as a plus bi, or c plus di for two complex numbers. And then when we add those together, we get a plus b, c plus I times b plus d, which is exactly what you would get if you just algebraically add and group like terms and then factor out the I. Multiplication is a little bit weirder because I squared equals -1, since I is a square root of -1. And that means that we have this a plus bi times c plus di eventually evaluates to ac minus bd plus I times ad plus bc. And again, you can just practice your algebra and verify that for yourself. And then the same with the exponentiation. You have a plus bi squared is really just a special case of multiplication because a plus bi squared is the same as a plus bi times a plus bi. So you can kind of just follow that same process. Okay, that was maybe a bit much, but take some time here and try and really understand what's going on in the complex numbers. There's a link that I will put in the description that will be helpful also if you're interested in further learning on the complex number front. But now we can kind of move into the implementation, which is complex numbers in GLSL. And this already starts to bring things back down to earth a little bit, because we can express these complex numbers as vectors in GLSL. And we are already comfortable working with vectors. We know how to do that. We've also already used matrices. And so we're basically going to implement all of this arithmetic for complex numbers using vector math in GLSL. So I have here kind of at the top, middle, this is essentially taking all of this and implementing it GLSL style using vector notation. So if we're adding two vectors, u and v, then we can just add them, u and v. And if we're going to multiply u times v, we can use this matrix to multiply by v, and u squared is just u times u, so we can do the same thing there. Now, for those of you that aren't familiar with matrix operations or matrices in general, I wanted to call that out a little bit more at the bottom here. So this is how matrix operations work, basically. So let's say we have a matrix A that's created from U. And so if our U vector has components A and B for our real and imaginary, we can create a matrix A out of that vector with A and B, and then minus B and A. And then if we have another vector V that is components C and D, we multiply A by V. Then we get AC minus BD on the top component and AD plus BC on the bottom. And that is actually the same thing as what's going on here. The only difference being this is refactored a little bit and still has that I term. This doesn't have the I term because it is implicit. So you have AC minus BD plus AD plus BC. And so that is my attempt at really, really fast going through how complex numbers work and how we can do arithmetic with them in GLSL. So now, how do we use that information to define fractals? As I mentioned before, every fractal set is defined by some expression, and we're basically going to test the convergence or divergence of an expression to determine whether or not that point is in our set. And if it's in our set, then it's part of our fractal, and if it's not in our set, then it's not. So different fractals may have substantially different set definitions. The one that we're going to be looking at first is the super classic Mandelbrot set. That set is defined by the set of numbers satisfying z n plus 1 equals z squared n plus c. And so basically, we need to find a way to program this expression, this equality, into GLSL and then test it for every point on our shader texture, basically for every pixel. So we're going to have this Mandelbrot set definition that we evaluate for every pixel. And that is going to help us determine whether or not that pixel's in our set. So here's the process. We will choose some boundary on the complex plane, b equals 2, for example. And what this boundary is really saying is, so if I go back here, we have our complex plane. So b equals 2 would be like drawing a little box right here and say, okay, so this is the complex plane that we're interested in. Or if b equals 10, then it would be this whole box. And so we basically say if based on our initial condition and a bunch of iterations, we will see if the equality stays satisfied throughout all of the iterations by testing it. And the way that we're going to do that is by using C as the coordinate of our pixel. So C is going to be our point coordinate on the complex plane, e.g. our pixel value. And so every iteration, we're going to say, okay, set Z equal to Z squared plus C. And then we're going to check that result against the boundary. If the absolute value of Z is greater than our boundaries after our n iterations, in this case 64, then our series is going to diverge, because that means that that point was not part of the set that belongs to our fractal. Okay, so this is probably getting a little bit heady. I'm going to try and use some better diagrams to make it clear. So here we have an initial condition C. So this C would be 0.3.1. And we can basically imagine each of these dots as one iteration. And so we can see that as the iterations increase, the dots are not really moving that far. They're staying within our plane. And that means that this initial condition point C is part of the Mandelbrot set because it is not diverging from that initial condition. However, this initial condition, 0.39.4, does diverge because as n increases, the kind of path that it traces moves far off of our plane. And so C is not part of the Mandelbrot set. And so this is what we mean when we talk about convergence and divergence. This is a converging series because the values of each iterative calculation become closer and closer together. And this is a diverging series because the values of each iterative calculation become further and further apart. So this one is inside our Mandelbrot set. This one is not. So taking all of that we've covered so far with our complex numbers and our defining of a fractal, and here is a very simple shader code for being able to set up the most basic type of Mandelbrot set. And so we can see here, we're defining our number of iterations, that's 64. We're defining our boundary, in this case 4. We'll set up a complex plane centered at the origin. This obviously vuv.st times 2 minus 1. There's a little bit of manual repositioning. You can tweak that on your own, as you'll see. And then here, so we're going to initialize our Z and our C. And then we'll have a for loop, which we now know how to do from our cellular noise section. And we'll use the for loop to basically implement this evaluation or equality every iteration. So Z equals, this is Zn plus 1, equals mat2 of Z, comma, negative Z dot Y, comma, Z dot X times Z plus C. And that should look pretty familiar because it is this calculation. So we're basically just doing complex number multiplication by to expand this Z times Z. And then on line 17 here, we are evaluating whether or not our series is converging or not. Here we're doing a little bit of a performance optimization by checking the Z squared against B squared instead of the absolute value of Z against B, because the absolute value is a expensive calculation. So it's easier to just say if B times B is greater than if Z times Z is greater than B times B, then we're out of our boundary, and therefore that point diverges. And then lastly, we say, okay, if I equals n, then the series converges. Then we want it to be black. And otherwise, we're going to use our number of iterations that it took to diverge as a coloration metric. And that's what leads to the really nice looking texture fractals that you've seen before. It's that coloring based on how many iterations it took to diverge, because something very close to the fractal will diverge differently than a point very far away from the fractal boundary. And then finally, how to improve fractal render quality. There's a couple things we're going to do. One, super easy, just defining a color palette. IQ's cosine palette that we've used in the past definitely works here. And that will be, I believe, part of the homework. Using a smoother iteration count, I've linked here this article from IQ that also goes in how to do that, and you can see the difference here. In this center image, the top obviously being the smooth and the bottom being the unsmoothed. And then finally, supersampling, which is functionally blurring. It's basically just calculating the value of each pixel multiple times and using an average. So, you might sample five different points that are very close to each other, just slightly offset, and use each of those to calculate an average, which will then be the color of that pixel. Again, examples of all of that forthcoming. So, that's the end of our slides. Now we can go back here into TouchDesigner and take a look at everything that we're going to be working on today. At this point, the rest of this lesson is going to be available on Patreon only. So if you're interested in following along, grabbing the project files and also the solutions to the exercises, make sure to head over to my Patreon now and subscribe. You can get the full video there as well as the project files. I mentioned this before, but the reason I do this is to maintain really high quality in this instructional content. And also, there's a lot of work that went into creating this course, and Patreon allows me to recoup some of that cost. So I appreciate the support for everyone who gives me their subscription dollars on Patreon. I know it's a big deal and not something that I take lightly. So with that, head over to Patreon, subscribe if you're not already a subscriber there, and catch the rest of this course. Okay, so for everybody else, let's get started and just jump into our code. So the very first thing, actually, let me turn off these viewers. Okay, so we can just grab this from scratch. And basically what I'm going to do is we're just going to kind of implement this edit contents. We're just going to implement this, and I already have it implemented here for you, but I think it's pretty nice. So let's see. Maybe I will move TouchDesigner over, and then move this over too. Very good. Okay. So now I've got this, and we can also view that. I'll make the shader a little bit bigger because I know that I'll want that. And then we can view. Okay, so that can be over here. And maybe this can be here for now. Okay, so pretty simple. First thing we're going to do is just do a define n, and we'll make that 64. And then we'll define b as 4. Now, I guess maybe actually I shouldn't have totally gotten rid of all of that. Define n 64 define b 2 or 4. Okay, so now first thing we gotta do is create that center. Then we'll initialize our vec2z is a vec2 0, and our vec2c will just be equal to our uv. And now this will be our iterator. For I equals 0, I less than n, I plus plus. And so this is going to be us doing the actual iteration. Z equals a mat2, z minus z dot y. And sorry, let me turn off my autocomplete here. And then finally, you say if the dot of z and z is greater than b times b, then we want to break. Now we say if I equals n, and what that means is if it took full 64 iterations and we never broke, that means I will be equal to n. And so if that is the case, then we want to just color everything 0, or black rather. And otherwise, we'll create a vec3 and we'll call it color, and we'll set it equal to a vec3 of I over n. And then we can just output our color with an alpha of 1 from our shader. And here is our fractal. And this is why I added UV minus equals vec2 0.5 comma 0. That's why I added this here, just to center our nice fractal on screen. And so there you have it. It is as easy as that to program your own Mandelbrot set. Now from here, the other things that I'm going to look at in our code today are just making some changes to this to be able to do some more interesting stuff. So the first thing that we want to do is add a continuous iteration to this. And so I'm going to open up, if you just give me a second, I'm going to open up here our IQ, and I will scroll to here. Okay, so this is the link that is linked in the slides. And this is the technique that we're going to want to work with. Now, to save some time, I'm not going to go through all the math here. It is also really well documented, and so I could absolutely not explain it any better than Mr. IQ explains himself. Now, what we do want very much is the implementation. And so the implementation, we're going to try and just kind of steal. So we can do that by looking into this. So this like simple little code here. Okay, so we have our iteration. Here's our z, right? Here, this should look pretty familiar. Z equals z squared plus c. Okay, and we already have that. And we already have this. Okay, so what we really need to do to make this continuous is define a float n equals 0 here. And then in our code here, we will have n plus equals 1.0. And then instead of having our color be equal to I over n like that, we're going to want to use this. And so here we could say instead float d equals this. And you can try the other one too to understand how the differences may work. And actually, I'm going to make sure that I output 1 for my alpha. And that doesn't look quite right, huh? So let's look at my pre-built example and see what I'm missing. Okay, so here it is. Okay, and then so we can say, all right, so basically you need to take this part. If n equals 1, set it equal to 0. And we also want to divide this by our n. D divide equals n. And then the last thing we'll say is if d equals 1, then d equals 0. And so this is now applying that smoothing continuous iteration, which, as you can see, definitely looks better. It's pretty nice. So the next thing that we want to look at is our infinite zoom. Infinite zoom like so. And there are a couple ways to implement infinite zoom, but the one that I have implemented right now is essentially just using a time offset for our lookup value. And converting that time offset to a zoom value that we then apply to our point coordinate. So let's go back to the shader that we're working on live here and see if we can just add this infinite zoom to our shader. So uniform float utime, we'll want to add that first. Utime abs time dot seconds. Okay. And then, okay, so here, C, let's have a float. We'll call it zoom equals cosine of u time. And then what happens if we just do this? Okay, so we can see right now we're kind of translating, which I suppose makes a little bit of sense. And we want to find some way to convert this so that instead of kind of panning like this, it's actually zooming in and out. So what if instead of plus, it's times? Aha. And now we have this cool zoom. Now, it's a little bit weird because it's maybe not zooming in on anything particularly interesting. And that's why I have this other infinite zoom setup where the selection of where we're zooming is a little bit more controlled so that it really, I mean, as you can see, like we're zooming in not just into the center where it's black here. And so we can try and do that again. So this would be like vec 2, 0.05, 0.05 plus UV times zoom. And so now you can see that we're kind of zooming into a different spot. And I think our zoom is also messed up because it's cosine is from -1 to 1. So we should say times 0.5 plus 0.5 to map that to 0, 1. And now we have a nice consistent zoom, but our locations may be a little bit funky. We can move it over. Maybe we actually want our U center to be a uniform vec2 called U center. And then we can grab this, add it to our C. And then, so what if this is 0 and this is something? And so here, now we can kind of have some more control over exactly where we're zooming in. And that is basically how you would do an infinite zoom. Now, there are ways to do it not oscillating, of course, but yeah, that's beyond the scope of this lesson at the moment. So that's your infinite zoom. We got the continuous iteration already, too. Now, the last two examples here, I am going to not rebuild completely, but rather just talk about. And these are a little bit more intense. I just wanted to include them because I wanted you to have examples in case you wanted to do some more advanced searching yourself. And so here, here we have basically a much more intense shader that includes Raymarching, because this is a 3-dimensional fractal that we're Raymarching to visualize. And so there's a lot going on that doesn't bear too much going into. Like, this is a bunch of SDF-based utilities. And what you really need is in this distance estimator. Okay, yeah, so here, this distance estimator function is the one that you're going to want to change if you want to implement your own kind of 3D fractal in here. So this is what is called in our Raymarcher. So you can replace whatever you want here, and as long as it's properly defined, we'll be able to Raymarch a nice animated 3D fractal. There is a ton of conceptual stuff that goes into like Raymarching and SDFs and doing all kind of like the 3D math that is going on here. So I'm not going to get more in depth than that. In our second GLSL course, there's going to be a lot more focus on some of these more detailed concepts and topics like Raymarching and that kind of thing. So for now, just take this as, let's say, like an added bonus, and also just something that looks really cool. Okay, last thing, or not last thing, next thing. Next thing is Supersample. So, wow, it's probably really impossible to see the difference here, but you can experiment when you have the project file on your own by changing this from 16 to 1, and you can see the difference in quality. So this is basically just implementing that Supersample, which we can see implemented here. Now, I actually don't love this aesthetic, I guess, with the Supersampling, but I did want to mention it because it's common in Fractal rendering, and it will just, I think, provide some good foundation. So this is our iterate function that is basically just refactored out into a function and directly ported from our other shader. And so to implement the Supersampling, we have this another for loop. Supersampling is also way more computationally intense because not only do we have our for loop that's executed 64 times for every pixel, but then we have a supersample. Okay, and so actually this iterate is executed on every supersample. And so that means we're executing that 64 times, or 100 and, or 1,000, 1024 times. So there's 1024 iterations. and there's 16 super samples. So we're executing all of this really, 1,024 times 16 times, which is a lot of times. Anyway, so what's actually happening here? Okay, so we have our UV, and then we have basically a random offset. So our UV plus equals this random offset, and then we multiply it by 1 over the pixel width to make it very small. Then we can scale. The period, translate it, etc. And that is basically just going to like jitter our domain a little bit. And also, so here, if we check it out, this will give us additional, what's the right term? Controls. So the period and translate just gives us additional controls, which will let us do more like domain manipulation things. Sorry, that was too much. You got to really just move tiny bits. And then for every iteration through our super sample for loop, we call that iterate. And then we accumulate our results. And then finally, we output our color divided by the number of super samples, which means we take the average. So that's how you would implement that. And of course, this is for the Mandelbrot, but this could be updated to be a Julia or anything else, and then you can implement the super sampling easily with any shader that you like. This is just the same shader, but colorized, which I am not going to go through because I do want it to be part of the homework. And so, yeah, I'm not going to go through how to colorize it because that's one of the exercises. And so I guess maybe that brings us now to the exercises. So exercises are to 1, apply a coastline palette or any other palette, but the coastline palettes are pretty easy, to the Mandelbrot set shader. Number 2, implement a smooth colorized Julia set shader. And that's good because it will require a little bit of, you'll have to take all the concepts that we learned and then figure out how to really like understand and use them, because you will need to implement a different logic here, because this logic is only for the Mandelbrot set. So that's really going to be the focus of that. Then I want you to animate that Julia set implementation. And then finally, this is more open-ended, use noise textures, domain manipulation, and anything else that we've done so far, along with Fractal shader to make something cool. And that is completely up to you, so have some fun with it. And that is everything for this lesson of Mastering GLSL in TouchDesigner. Thank you so much for your support, and until next time, happy creating.